which is a pipeline 5 sleep staging. Okay, and yeah, I'm going to install the current development branch PyHealth. It takes like 5 seconds. And I already, because this is an open data set, I already store the data into our cloud storage. And then right now in this Jupyter, I'm going to download 3 patients recording. This is the first patient recording, the PSG file with the hypnogram file. And this is the second one, this is the third one. And yeah, the data will be stored in this folder, storage license, this 6 file, okay? And yeah, so basically we can access the data, use this link. Okay, and I'm going to show you the structure of the data. And to access the data, we have to use this MNE package to read the raw EDF data. And yeah, I'm going to run it. Okay, so this is the raw data, which has 7 channels and how many? 7, almost 8 million like time steps. And the sampling frequency is 100, as mentioned. SleepEDF. As mentioned in the dataset, I believe it's 100. Yeah, sampling frequency 100. Okay, that means the recording time is like this many seconds divided by 60, divided by 60 again. Then will be the hours that this recording lasts. And then I'm going to read the annotation file associated with this sample, okay, which is the hypnogram file. Still use the package NME, and this hypnogram, this annotation has 2 attributes. One is duration, one is description. So it's probably hard to like read here. I can roll it more clearly.
This MNE package is a standard Python package for?
Yeah, it's a standard Python. It's a standard Python package to load the PSG data.
Okay. You mean for this EDF file, they have a...
Yeah, for this EDF file.
So are all the EG data stored in the EDF file, or this is specific for sleep?
For that, I'm not very sure, but I mean, even the data Brandon gave us is not in this EDF file. Different like devices might opt with different format. Okay. But I believe this EDF file is like a very commonly accepted format for PSG file, PSG data.
And this particular package, MNE, is this specifically for EEG processing, or?
I think it includes all different biosignals. Can be for ECG or EMG, EOG, EKG.
Oh, okay.
Yeah.
So do you use that package in your in part of this PyHealth implementation for Biosignal?
Yeah. We need that. We need that to load this EDF file.
Okay.
So we actually use this. This is the documentation for PyHealth, and there are different data sets. So we only going to the development. We only use this MNE package for this SleepEDF data sets. But if you have a different EEG data or ECG data used for into the PyHealth, then probably you have different packages to process the raw EEG data or ECG data, because they are stored in different formats, not necessarily like .edf file.
For example, one step I remember, you have to compute spectrogram, right?
Oh, that's the later part. That's in the model.
But that's not part of the this package.
Yeah, that's not part of the package. This package is only to read the data from .edf file to a matrix in Python. That's it. done. Yeah. So yeah, I'm going to explain this annotation file. So this annotation file tells us, okay, in the first few, so this is the time. So in the first this much time, this is the label. The patient is basically awake, not fall asleep. And then the next 120 seconds, this patient is in sleep stage 1. And in the next 390 seconds, the patient is in sleep stage 2. So what we will do is we segment this signal into 30 second times 100 frequency. This will be the first signal, first 30 seconds epoch. Okay, then how to get the label? The first label will be sleep stage W. That's it. That's the first sample. Okay, and the second sample will also be sleep stage W, and then so on and so forth until we pass this time range to the next range. Okay, then all the labels will belong to this sleep stage 1. So for sleep stage 1, it only covers 4 epoch because 30 seconds is the duration for 1 epoch. Okay, that's how we get the samples. We split this time range into 30 seconds, 30 seconds, and then we have a label for that 30 seconds. And then we also split the signal into 30 seconds, 30 seconds. We can match the signal with the labels. Okay, so this is the whole data structure for this data set.
Yeah, this is just specific for the data set. I remember for the MGH data, the stages are different, right? They only have I assume the stage 1, 2, 3 correspond to N1, N2, and 3, or
yeah, N1, N2, N3, and we have a.
We also have a 4, right? So I assume that this stage, this definition of stages are kind of different from the another data set, right? That for example,
we also have 4.
Right. No, I mean I think for some other data set, the
MGH. For MGH, they only have 1, 2, 3. They only have W awake, 1, 2, 3, and R. Yeah, R. REM stage, rapid eye movement.
So I wonder, there's some mapping, or like a 3, 4 all map to 3 in that case, or do we?
We can do that, but I didn't do that in this specific data set.
Separate, so we train models separately. There's no. Somehow I remember we train on one data set, test on another. That's also happened.
But that's other projects in transfer learning or like pre-training task. But I do remove the channel is also different. Yeah. And the number of channels are also different.
But can we still do that type of transfer across if the channels are different?
Yeah, we can do transfer across.
I guess
but that
one-dimensional.
That's need like novel models.
Okay. Anyway, I think that's a digression.
Yeah, that's a separate like discussion. But for this data set, I do delete this segment that has like these question mark labels. And yeah, that's for the data description part. I haven't started the pipeline yet. Okay.
You usually also filter the EEG data, make an independent component analysis because of the crossover of the signals, from the different channels. This is done by the MNE when you read in the data and make the matrix. This is part of that step.
Not sure. Sorry. I think there's probably some pre-processing can be done. That's what George is saying too.
They probably already do that. But I mean, I have to carefully read their description.
Are you saying doing ICA?
I didn't do ICA on this.
But George, I think this is probably like a very basic pipeline. You could probably enhance.
So all these different metrics, like pre-processing or what, can also, I think in this package we will include that pre-processing as part of the model parts. But for this data processing, we wanted to keep all the raw file for the data there, because probably different downstream model, they have their own considerations. They wanted to do different like pre-processing. We don't want it to break, like drop some information.
Yeah, I think Brandon mentioned some specific parameters that they are using, to set up the filter.
Oh, they use bandpass filtering because their device has that specific band noise, so they filter that. But different device can be different.
That's actually an interesting question, right? You have this basic pipeline, Chaoqi. For George want to add some additional pre-processing, which component, which part of this PyHealth he should change, right? To add those pre-processing.
The pre-process can be added in different part, but to make it clear, I think the pre-processing should be added in front of the modeling parts after we processing the after we got the data loader, yes.
Right around there, like after load the raw data, maybe pre-process all in that part.
Yeah, I think there are different ways or options to handle data processing or missing feeding stuff.
Yeah, maybe that's a good space, right? Because I can imagine those pre-processing can be expensive and maybe makes sense to do it one time. And assuming this the extra storage is not a big constraint, then all the pre-processing happen once. I guess you can cache them, right? Or write it to the folders. Then you can later on just read those pre-process the data.
Yeah, that's also possible. But yeah, today I will just introduce a basic pipeline. So after we introduce the data specifically for this SleepEDF data, and I'm going to show you the 5-stage pipeline. Stage 1, to load the data. We use a SleepEDF dataset. So this, whatever I just shown you here, and MNE read the EDF file or the annotation files is already implemented in this SleepEDF specifically for this dataset. This API is specifically for that dataset. You just give us the root to the data. Right now, this root only contains 3 patients recording. We can run it. It's pretty fast. Okay, and then you can use .stats to show the statistics. Here we have 3 patients recording, and each patient only has 1 recording. So in total, 3 recordings. Okay, and then we can access what is inside of this SleepEDF DS. You can just say SleepEDF DS dot patients. Okay, this is always stored in this object. I can show you this. So this is a patient ID, the first patient ID. You can use it as a dictionary and then access patient ID. Okay. So this patient only has 1 recording. So in this list, it only has 1 JSON inside of it. And in that JSON, what we have the loading path for the data. This is the folder path. And then we have a signal file, which is this one. We have a label file, which is annotation file, hypnogram. And then this is the path, like the cache path. We are going to save our later on small segments into. And then this hash folder name is computed by our program. So the data is still in the disk. We only load the path for the data into the memory. Okay. In the second stage, we're going to design this sleep staging function. We set this function to this data set, which will load the whole recording, long recording into memory, split the recording to 30-second segments, and then save the segment back to the cache folder, to this cache folder specified by this save to path. I'm going to run it. It can be a little bit slow because in the Google Colab, it only has 1 GPU. Although we implement this parallel loading.
Can you show the implementation of that function, the sleep staging?
Yeah, I can show the implementation, but let's first look at the statistics. So after this processing, we got this many segments, 7,000, almost 8,000. And then I can show you, this is actually the folder for that whole segments. I can show you whether they are really stored in that path. I can use that. I can list them, but it's too large. And I use W. Let's see. I can show the head first 10 file. this. So these are the segments I stored. I can actually load one of them to prove that they are segments. Pico.load. This is the folder name. And then we pick one of them, for example, this one. Okay, this is a sample. Load them. Okay, sorry. I should use read binary file. Okay, we got a sample. Let's see what is inside of the sample. It has a signal and it has a label. And what is the size of the signal? It's 7 channel, 30 second, and like times 100 sampling frequency. So that's like basically the sample we stored in the folder. And there are like almost 8,000. See, this is the number of the sample stored under that folder from 3 patients. Okay, I'm going to delete this. Yeah. So yeah, I will going to show these task functions later. Let me maybe first finish this pipeline. And after we obtain these samples, we use our, okay, so let's show this. So all the samples are still stored in the disk. Although we process them, but we still store it in disk. What is in the memory is this. So the first sample in the memory is like this. We have the patient ID, the recording ID, and the epoch path. So this is the sample path. It's only when we get into these data loader parts, only when we wanted to use these samples to train the models, we will load the data from the disk to the memory. So this what is in the memory, this object is still very small. It doesn't contain any like sample information. But from this code itself, you can tell the difference from this EHR pipeline. Let's run it. Why I want to do this, I want to evenly split them into a training, validation, and test, because we only have 3 patients. So and then if I can do an experiment. If I split into 0.8, 0.1, 0.1, and we split it by patient, that means all the patients will go through the training sets. Although we can run it through, but I can show you the length of the training order. This is a batch size, which is the all samples divided by the this is the number of batch divided by the batch size. So what is inside of the validation order is 0. It has 0 batch because all the patients are classified into the training data set. So we can do an even split. So in the training, we only have 1 patient data. In the validation, we only have 1 patient data, and in the test, we only have 1 patient data. Okay, then we can define a machine learning model.
Sorry, I missed. I missed one thing. So this automatic storage in the cache, when you train the model, what function takes care of that? This loading and unloading to actually train this model. You know, you have the function from Python from the algorithm, but who controls or what controls the unloading and the loading of the different of the data?
Is
it somewhere involved?
It's our data loader. It's actually this. I can show you the code here. But it's very quick. I can copy the code over, and then.
So, but it is basically comparable if I would have the entire data in the RAM and run my model. Okay.
Yes, it's comparable, but you can't have entire data in the RAM because it's just so large.
So that's why you build that.
This part actually take care of it. Let me show you. This is for each R, not that. We wanted to find the one for signal data, which is the get item. Okay, this is a part. I can copy it over and explain to you.
No, you don't have to.
Yeah.
I want to. slow you down. I just wanted to know. Okay.
No problem. Yeah, I can show you one example and see whether we can use the code I just copied to transform it. So the samples here is the SleepEDF task ds.samples. Okay, so this is the samples in memory, right? When we use this get data loader to get the actual samples for machine learning model, we will like wrap the code. We will wrap the this part of the code on top of the sample. So this is basically the sample. You can replace it, and then load sample copy. Yeah, and then
so
I
and
can
this
show you what is the
this works.
sample.
This works on any server, or is this hardware dependent?
No, this works on any server. Doesn't depend on hardware. If the hardware supported Python, then our code can run. So
okay.
you can see after this part of the code, whenever you load a data sample into the data loader, this is the input of the data loader, and this is the output. What changing here? The record doesn't change. The patient ID doesn't change. What changed here is we drop this epoch pass. We drop the pass to that sample, but we replace it with the signal.
Yeah.
That's the actual signal. And yeah, I can stop it. So so our loader, get loader, will taking care of that part of the code to transform to get the samples from this sample pass, and then get the actual sample. Then we define machine learning. Yeah, I shouldn't delete that. Undo delete. Okay, this is the sample. And then when you define a machine learning model, this is the model we want to define. And then we just give the model the data set, and then tell the model what is the feature of our model. The feature key is signal, because our feature key is actually signal, and our label key is the label, which has one-to-one correspondence. But these names are customizable, and these names are actually defined in this task function, which I will going to show you after I finish this pipeline. Okay. Yeah. Then we define the model. The model computes some statistics, model dependent statistic, which is what is the input channel to 2D convolution network, what is the output channel, and other specification for the model layers. We don't need to care. We don't care, because the model already take care of it. And then we train the same training code for EHR and for signal. And we just train it, then running the epochs. And after we train it, we test the code, use the usual testing method, evaluation, or inference. So we can check 2 epochs. The first epoch loss function, loss value is 0.7. And for the second epoch, loss is 0.5. Although we only have 1 patient for the training, but loss decreased very fast. Yeah, decrease again. So that's basically finished this pipeline, and we can check the result later. But now I can show you what is the definition of our task function. It's easy to check if you go to our website and then click task. There are several tasks for EHR prediction, drug recommendation, readmission prediction. Here, what we care about is the sleep staging task. And this is the source code for that task function. Yeah, and there are some description for the task definition and the argument needed. What is the return? And I can explain to you here. Let's check the result first. Okay, we finished the training, and okay, we finished the evaluation. 2 different options to evaluate the model. Let's go to this sleep staging task. So this task function will take a record in a patient's lung recording in, and there's one parameter called an epoch segment, saying that we will segment each 30-second range as 1 epoch. One epoch basically means 1 segment. And you see the hyperparameter. Okay, that signal, that row EEG has a 100 Hertz as the sampling frequency. And then we first get the root, the PSG file, and the hypnogram file, and the safe path. So we already see this, right? We already see this here.
So the
We already see this here.
So the sampling rate, should we make it a parameter as a argument in that function, as opposed to right now you set it inside the.
Oh yeah, because this like function is only for SleepEDF. I mean, we can also design like ECG task, but the epoch second might be different. So we can also move these sample rates to like up as an argument. But the point I want to make is that this
so this
function is only for SleepEDF data sets.
Okay.
Yeah. So this part, what we are doing in this part is mapped to what we have shown here. After we finish the first step, before setting the function, we are going to define function. Before setting the first function, what we have is for each patient, we have the load from path, we have the signal file, we have the label file, we have what path to save. We have this full information. And we actually extract this information out to store it in this full object. And then the first 6 character will define the patient ID. That means, so this is the file name, and the first 6 character is the patient ID. This one is the patient ID. And this E0 is some other identification in your data set, but this one is actually the patient ID. So this is very delicate, like very specific for one data set. And yeah, we use the same method, MNE, to load the data. And then got data basically give you the signal, which is this X is basically this X has this size, okay? And then we got the labels, we got the duration and the description. We actually split the duration into 30 seconds, and then unroll these labels into a very long list. Okay, this is how we get the list of labels. And then we wanted to segment X and then find its corresponding label. Segment X and find the corresponding labels like in this loop. And of course, if the label is not in these 5 labels, we will drop the segment. So we slice X to a 30 second. We got the epoch signal. We got segment, and this is segment label. We find the label actually, and we only use the last character to denote the label. We don't want to store this repetitive sleep stage space, this very long string. So we only use the last character. We use -1 to get this character. Okay, then use this save to pass. We this is the format of the sample name, patient ID, dash this slice index be the example name corresponding to the sample name is where's the sample? I can show the sample here. List this add them. Okay, the sample name actually have that structure. This is this patient ID dash the segment ID, okay, which is defined in the task function. And then we dump the signal and label to disk, but we store this path to the samples and then keep it in the memory. So these samples is actually the one we get from from this one. Let me show you whether the keys matches. the record ID, patient ID, and epoch underscore pass, and the label, it matches, right? And done. We are done with defining the function. Right, that's how we define it. Also, it's a little bit like confusion, maybe confusing. Maybe I go like these 2 pages back and forth. But
okay, Chaoji, thanks for explaining these details. If you go back to your pipeline, and method you are using is like a one self-supervised learning, right?
Yeah, the method I'm using is yeah, if you want to take a look at the message, just check this model and ContraWR. And then so this is the method. So this ContraWR is actually the encoder model for this ContraWR. And this model is like our previous paper in arXiv. Although it's a self-supervised model, but we borrow the encoder part as the supervised model in this pipeline.
Okay, so this is not a.
This is not a self-supervised. Okay. We just drop the last layer and change the loss function, not the self-supervised loss anymore. We use a cross entropy loss to do the supervised classification.
Why don't we just implement some? Is it just like a CNN here, or
this is a yeah? We can take a look at details of the model. So it's like this is the basic unit of the model, which is a convolutional block, residual ResNet block 2D, and then the model itself called ContraWR is itself a just read this forward function. It first transform the NumPy data into tensor. Okay, that's the first step. Second step is to get the spectrogram of the data, which is implemented by this torch STFT. This part. We first compute this short time Fourier transform of the data, transform it from this format to this format. Okay, and then we apply the encoder. And if you want to take a look at the encoder, where it goes back. The encoder is where is this? The encoder is here. Encoder is a stack of multiple ResNet 2D convolutional blocks.
Okay, so in some sense, it's more of like a
spectrogram plus some multi-layer of convolutional neural network.
Okay, it's a CNN over the
spectrogram.
Okay, I think that makes sense. It may be worth just explaining that in Word in that method part instead of saying coder part of that self-supervised learning.
Oh yeah, we can definitely like provide more information on this.
Because this is a little bit confusing, because when I read this, I thought, okay, are you doing self-supervised learning? But it turns out it's more like if you say CNN, it's probably more correct, right?
Yeah, that's true. But like different models are based on C and.
Yeah, but at least it's a supervised model, right? But
yes, a supervised model.
Self-supervised, so it's maybe confusing for.
Yeah, sure. We definitely can provide more like descriptions for the model. Yeah, that's basically it. If you think our like this PyHealth session and this Jupyter notebook is very helpful for you to understand, to study, to implement your pipeline, please give us a star at our GitHub repo. And then, yeah, this